dear viewers, the title of my lecture is Applications of Laplace Transformation. In order to show the real power of Laplace transformation in its applications to various problems of engineering mathematics, we shall derive some more properties of the Laplace transformation. Two very important properties of the Laplace transformation concern the shifting on the s axis and the shifting on the t axis. The shifting on the s axis we had covered in our previous lectures on Laplace transformation, where we had shown that if the replacement of s by s minus a in f s, which is the Laplace transform of the function f t, corresponds to the multiplication of the original function f t by the exponential function e to the power a t. In the second shifting theorem, which concerns the shifting on the t axis, we shall show that the shifting, if we replace t by t minus a in the function f t, then it corresponds roughly to the multiplication of the Laplace transform f s of f t by e to the power minus a s. The precise formulation of the second shifting theorem is as follows. It says that if L f t is equal to f s, where s is greater than gamma, then e to the power minus a s into f s, a greater than or equal to 0, is the Laplace transform of f t minus a into u a t, where u a t is the unit step function defined as u a t is equal to 0 when t is less than a, and u a t is equal to 1 when t is greater than or equal to a. This is the graph of the function u a t. In the interval 0 to a, that is when t lies between 0 and a, u a t is defined as 0, and when t is greater than or equal to a, u a t is defined as equal to 1. Let us look at the proof of the second shifting theorem. The Laplace transform of f t minus a into u a t by definition can be written as integral over 0 to infinity e to the power minus s t into f t minus a into u a t dt, which is equal to integral over a to infinity e to the power minus s t into f t minus a dt, because u a t is equal to 0 over the interval 0 to a, and over the interval a to infinity it is defined as 1. So, the integral over 0 to infinity reduces to the integral over a to infinity, and u a t becomes 1. Now, let us make a substitution here. Let us put tau is equal to t minus a. So, when we put tau equal to t minus a, the limits of integration change from a to infinity to 0 to infinity, and dt becomes equal to d tau, and hence we get L of f t minus a u a t equal to integral over 0 to infinity e to the power minus tau plus a into f tau d tau, which can be written as e to the power minus a s integral over 0 to infinity e to the power minus s tau into f tau d tau. Now, integral over 0 to infinity e to the power minus s tau into f tau d tau is the Laplace transform of the function f tau. So, we can say it is equal to f s, and thus we get the Laplace transform of f t minus a u a t equal to e to the power minus a s into f s. Now, if we take a particular case here, let us assume that f t is equal to 1 for all t greater than or equal to 0, then we will have the Laplace transform of f t minus a into u a t equal to Laplace transform of u a t, because f t is equal to 1 for all t greater than or equal to 0. So, we get Laplace transform of u a t equal to e to the power minus a s into Laplace transform of f t, that is Laplace transform of 1. We know that Laplace transform of 1 is 1 by s whenever s is greater than 0. This we have shown earlier in our previous lecture on Laplace transformation. So, the Laplace transform of u a t will be equal to e to the power minus a s over s whenever s is greater than 0. Now, let us study a remark. Quite often we have to find the Laplace transform of f t into u a t, where the function f t lacks the shifted form f t minus a. If we have f t minus a here, in place of f t we can directly apply the second shifting theorem, but quite often it is not so. instead of f t minus a we have f t, and we have to find the Laplace transform of f t into u a t. So, in such a case we do the following: f t into u a t may be written as f t minus a plus a into u a t. Now, f t minus a plus a is a function of t minus a, which we have denoted by capital F t minus a. So, we get f t into u a t equal to f t minus a into u a t, and then by the second shifting theorem, that is theorem number 1, Laplace transform of f t into u a t will be equal to Laplace transform of f t minus a into u a t. Now, Laplace transform of f t minus a into u a t by theorem 1 is e to the power minus a s into Laplace transform of the function capital F t, which is equal to e to the power minus a s into Laplace transform of f t. F t is equal to f of t plus a, because we have assumed that capital F of t minus a is equal to small f t. So, f of f t is equal to f of t plus a. So, we get the Laplace transform of f t into u a t equal to e to the power minus a s into Laplace transform of f t plus a. So, whenever we want to find the Laplace transform of the function f t into u a t, what we will do is we will write it as e to the power minus a s into Laplace transform of f t plus a. In the second shifting theorem we had f of t minus a here and we had f t here. Now, the change is that we have f t here and here we have f of t plus a. So, we get the Laplace transform of the function f of t plus a. In the function f t we replace t by t plus a and then find its Laplace transform in order to get the Laplace transform of the function f t into u a t. Now, let us study an example based on the second shifting theorem. Let us find the Laplace transform of the function f t, where f t is defined as 0 for t less than pi by 2, f t is defined as sin t for pi by 2 less than or equal to t less than 3 pi by 2, and f t is defined as 0 for t greater than or equal to 3 pi by 2. So, we can write the function f t in terms of unit step functions as f t equal to sin t into u pi by 2 t minus u 3 pi by 2 t, because when t is less than pi by 2, u pi by 2 is t is 0, u 3 pi by 2 is t is also 0. So, f t is equal to 0, and when t is equal to pi by 2 or more than pi by 2, but less than 3 pi by 2, then u pi by 2 t will be equal to 1, while u 3 pi by 2 t will be 0. So, f t will be equal to sin t, and when t is equal to 3 pi by 2 or more than 3 pi by 2, u pi by 2 t will be equal to 1, u 3 pi by 2 t will also be equal to 1. So, f t will be equal to 0. Hence, f t, the given function f t can be described in terms of unit step functions u pi by 2 t and u 3 pi by 2 t as f t equal to sin t times u pi by 2 t minus u 3 pi by 2 t. Now, let us apply the second shifting theorem. So, when you take the Laplace transform of this, by linearity property of the Laplace transform, L f t will be equal to L of sin t into u pi by 2 t minus L of sin t into u 3 pi by 2 t. Now, we can see here that this is L of sin t into u pi by 2 t is not actually in the form of the second shifting theorem, rather it is in the form of the remark which follows the second shifting theorem, where we had discussed that how to find the Laplace transform of f t into u a t. So, using that remark we will have the following: Laplace transform of the function f t will be e to the power minus s, a is pi by 2 here. So, e to the power minus pi s by 2 into Laplace transform f of t plus a, f t is sin t, a is pi by 2. So, Laplace transform of sin t plus pi by 2 we have minus e to the power minus s, a is 3 pi by 2 here. So, we get e to the power minus 3 pi s by 2 into Laplace transform of sin t plus 3 pi by 2. Now, sin t plus pi by 2 is cos t. So, Laplace transform of cos t we have here, and then Laplace transform of sin t plus 3 pi, sin t plus 3 pi by 2 is equal to minus cos t. So, we have minus plus here, e to the power minus 3 pi s by 2 into Laplace transform of cos t, and Laplace transform of cos t we know it is s over s square plus 1. So, we get the right hand side as e to the power minus pi s by 2 into s over s square plus 1, plus e to the power minus 3 pi s by 2 into s over s square plus 1, which is further equal to s into e to the power minus pi s by 2 plus e to the power minus 3 pi s by 2 over s square plus 1. Let us take another example on based on second shifting theorem. Here we have to find the inverse Laplace transform of s into e to the power minus s by 2 plus pi into e to the power minus s over s square plus pi square. We can express the inverse Laplace transform of s e to the power minus s by 2 plus pi e to the power minus s over s square plus pi square as the sum of the inverse Laplace transforms of s into e to the power minus s by 2 over s square plus pi square and pi into e to the power minus s over s square plus pi square. And we know that s over s square plus pi square is the Laplace transform of cos pi t, and here we have, if you identify with e to the power minus a s here, s into e to the power minus s by 2 tells us that a is equal to half here. So, we have to find inverse Laplace transform of e to the power minus a s into f s, where a is half and f s is s over s square plus pi square, whose inverse Laplace transform is cos pi t. And so, by second shifting theorem, inverse Laplace transform of s into e to the power minus s by 2 over s square plus pi square will be u a t becomes u half t into f t minus a. F t minus a means f t is cos pi t. So, f t minus a will be f t minus a will be f t minus half, that will be giving us cos pi t minus half. And then we have inverse Laplace transform here of pi e to the power minus s over s square plus pi square. Pi over s square plus pi square is the Laplace transform of sin pi t function, and e to the power minus a s tells us that a is equal to 1 here. So, using second shifting theorem, we get u 1 t, that is u a t becomes u 1 t and then f of t minus 1. So, f t is sin pi t. So, f t minus 1 becomes sin pi t minus 1. So, we get the inverse Laplace transform as cos pi into t minus half into u half t plus sin pi t minus 1 into u 1 t, which we can write in the simplified form as cos pi t minus half becomes sin pi t into u half t, and sin pi t minus 1 becomes minus sin pi t, and so we get minus sin pi t into u 1 t, and we can simplify it further. We can write it as sin pi t times u half t minus u 1 t. Now, let us take another function f t, which is defined as 0 when t is greater than or equal to 0, but less than pi by 2, and equal to cos t when t is greater than or equal to pi by 2, and let us find the Laplace transform of this function. So, again we can express this function as in terms of unit step functions. We can write f t as cos t into u pi by 2 t. When t is less than pi by 2, u pi by 2 is 0, u pi by 2 t is 0. So, f t becomes 0, and when t is equal to pi by 2 or more than that, then u pi by 2 t is equal to 1. So, we get f t equal to cos t, and then Laplace transform of cos t into u pi by 2 t will be equal to e to the power minus a s. A is equal to pi by 2 here. So, e to the power minus pi by 2 into s, and then Laplace transform of f t plus a. F t is cos t here, a is pi by 2. So, we get Laplace transform of cos t plus pi by 2, and cos pi by 2 plus theta we know this is equal to minus sin theta. So, we get minus L sin t, L of sin t here. So, we get minus e to the power minus pi by 2 into s L of sin t, and sin L of sin t is 1 over s square plus 1. So, we get minus e to the power minus pi by 2 s over s square plus 1. Now, we are going to study periodic functions. Periodic functions occur in many practical problems, and in most of the cases they are more complicated than the single sine or cosine functions. We are going to show that if the function f t is periodic with period t and it is piecewise continuous over a length t, then the Laplace transform of the function exists. So, let us define first a periodic function. A periodic function f is defined, a function defined for all t greater than 0 is said to be periodic with period t greater than 0 if f of t plus t is equal to f t for all t greater than 0, and if f is periodic with period t, then we can easily see by induction on n that f of t plus n t is equal to f t, where n takes values 1, 2, 3 and so on. Now, for such a function we have L of f t equal to 0 to infinity e to the power minus s t into f t dt. We shall see that for the existence of the integral of a periodic function with period t, we just need the piecewise continuity of the function f. So, let us see how when this Laplace transform of the function f t exists. So, for the periodic function L of f t can be written as integral 0 to infinity e to the power minus s t into f t dt. And now, using periodicity, what we will do, we will break the interval 0 to infinity into parts 0 to t, t to 2t, 2t to 3t and so on, and make use of the periodicity of the function f t. So, what we will do in the second integral onwards on the right side, that is integral t to 2t, integral 2t to 3t and so on, we shall make substitutions t equal to tau plus t, t equal to tau plus 2t, t equal to tau plus 3t and so on, and use periodicity of the function f to obtain L f t is equal to integral 0 to t e to the power minus s t s tau f tau d tau plus integral over 0 to t e to the power minus s tau plus t into f tau d tau. Here when you substitute t equal to tau plus t using periodicity of the function f, f tau plus t will be f tau, e to the power minus s t will become e to the power minus s tau plus t, and dt will become d tau. The limits of integration which are t and 2t will change to 0 to t. Here they will become 0 and t, and in the integrand we will have e to the power minus s tau plus 2t into f tau d tau, again using periodicity here. This way we shall then have L f t equal to 1 plus e to the power minus s t plus e to the power minus 2 s t and so on, multiplied by integral 0 to t e to the power minus s tau into f tau d tau. Now, this is a geometric series, the ratio is e to the power minus s t. So, we can write the sum of this series as 1 over 1 minus e to the power minus s t, and then multiplied by integral 0 to t e to the power minus s tau f tau d tau. This integral which occurs here exists if f t is a piecewise continuous function, and of course, periodic with period t. So, thus we have the following theorem for a periodic function. If f t is a piecewise continuous function having a period t greater than 0, then the Laplace transform of the function f t exists and is given by 1 over 1 minus e to the power minus s t into integral 0 to t e to the power minus s tau f tau d tau. Let us take an example on this article. Let us find the Laplace transform of the square wave function, which is shown here in this figure. You can see here that the function f given by this figure is periodic with period 2a here. You can see the graph of the function over the interval 0 to a, it takes the value a, and then over the interval a to 2a, it takes the value minus a, and then the graph of the function f over the length 2a is repeated over from 2a to 4a and so on. So, it is a periodic function with period 2a. The given function is periodic with period we have denoted by t. So, t is equal to 2a here. Hence, f t is clearly a piecewise continuous function on the length t equal to 2a. So, Laplace transform f t of the function given function exists and will be obtained from this result 1 over 1 minus e to the power minus s t integral over 0 to t e to the power minus s tau f tau d tau. So, t is equal to 2a gives us Laplace transform of the given function f t as 1 over 1 minus e to the power minus 2a s, and then integral over 0 to 2a is broken up into two parts, integral over 0 to a and then integral over a to 2a integral over 0 to a, we have in the integral over 0 to a we use the definition of f is equal to a in this part of the interval, and in the interval a to 2a function f takes the value minus a. So, we have put those values of f, and then we integrate e to the power minus s tau. Integral of e to the power minus s tau with respect to tau gives us e to the power minus s tau over minus s, and so when you put the limits 0 a here and a and 2a here, what we get is the following: a times 1 minus 2 times e to the power minus as plus e to the power minus 2as over s into 1 minus e to the power minus 2s. Now, 1 minus 2 e to the power minus as plus e to the power minus 2s is the square of 1 minus e to the power minus s. So, we replace this numerator by a times 1 minus e to the power minus as whole square. In the denominator we have s into 1 minus e to the power minus 2s. 1 minus e to the power minus 2as can be factorized as 1 minus e to the power minus s into 1 plus e to the power minus s, and then 1 minus e to the power minus s can be cancelled from the numerator and denominator, and we will be getting a times 1 minus e to the power minus s over s times 1 plus e to the power minus s. Now, if you multiply in the numerator and denominator by e to the power as by 2, then what we will get? A over s times e to the power as by 2 minus e to the power minus as by 2 divided by e to the power as by 2 plus e to the power minus as by 2, which we know that denotes the tan hyperbolic of as by 2. So, we have the Laplace transform of the given square wave function as a over s into tan hyperbolic as by 2. Now, we are going to discuss the Dirac delta function. The Dirac delta function is also called the impulse function, and has applications in these problems where a large force occurs is applied over a very small for a large force is applied for a very short time. Say for example, in the case of bending of beams, when we use the point loads, the point load means we are applying a very large pressure over a very small area. So, in such cases we use the Dirac delta function, which Dirac delta function is also called as unit impulse function or impulse function, and it was introduced by British theoretical physicist Paul Dirac. So, it is applied or used in problems where a large force is applied for a very short time, or a large force acts over a very small area, for example, in the loading of a beam. And because of its nature, it is defined as delta t minus a is equal to infinity at t equal to a and 0 when t is not equal to a. So, and further that integral of delta t minus a over the interval minus infinity to infinity is defined as equal to 1. We are going to show that the Laplace transform of delta t minus a exists and is equal to e to the power minus as for all a greater than or equal to 0. So, let us consider the function delta epsilon t minus a, which is defined as 1 over epsilon for t bigger than a and less than a plus epsilon and 0 elsewhere. Let us look at the graph of this delta epsilon t minus a function. Delta epsilon t minus a function by its definition can be drawn like this t axis, this delta epsilon t minus a representing that vertical axis, and then we have over the interval a to a plus epsilon delta epsilon t minus a taking the value 1 by epsilon and 0 elsewhere. So, this delta epsilon t minus a is then the derivative of the function u epsilon t minus a, which is defined as 0 for t less than a and 1 by epsilon times t minus a for a less than t less than a plus epsilon and 1 for t greater than a plus epsilon. Clearly, you can see that the derivative of u epsilon t minus a gives us delta epsilon t minus a. So, the graph of u epsilon t minus a is like this over the interval for values of t less than a, it is taking value 0 over the interval a to a plus epsilon, it is given by this line segment, 1 by epsilon t minus a having slope 1 by epsilon, and then over the values of t greater than a plus epsilon, it is taking value 1. Further, we note that as epsilon tends to 0, u epsilon t minus a tends to u a t, that is the unit step function, which is 0 for t less than a and equals 1 for t bigger than or equal to a. And that is why we can regard delta t minus a as the derivative of u a t. Delta t minus a was the limit of u epsilon, delta t minus a was the limit of delta epsilon t minus a, delta epsilon t minus a was the derivative of u epsilon t minus a. So, and the limit of u epsilon t minus a as epsilon tends to 0 is u a t. So, we say that delta t minus a is the derivative of u a t, and since it is the derivative of u a t, we can write it as u a t equal to integral over minus infinity to t delta t minus a dt. Now, if f is assumed to be continuous at t equal to a, then from the mean value theorem of integral calculus, we will be getting integral over minus infinity to infinity f t into delta epsilon t minus a dt equal to f t into 1 by epsilon dt, because delta epsilon t minus a assumes value 1 by epsilon over the interval a to epsilon a to a plus epsilon, and elsewhere it is defined as 0. So, this integral is equal to integral over a to a plus epsilon f t into 1 by epsilon into dt. Now, let us use the mean value theorem here. If we assume that f is continuous at t equal to a, we can apply the mean value theorem of integral calculus, and then this will be equal to 1 by epsilon is a constant, we have put the constant out here, and then a plus epsilon minus a plus epsilon minus a into the value of the function at some intermediate point. Theta is an intermediate point of the interval a to a plus epsilon. So, where theta is some point in the interval a to a plus epsilon, and then let us now take, let epsilon go to 0. When epsilon goes to 0, we shall have delta epsilon t minus a tending to delta t minus a. So, we will have the left hand side tends to integral over minus infinity to infinity f t into delta t minus a dt, while the right hand side epsilon will cancel with this epsilon, f theta will tend to f a as epsilon tends to 0. So, the value of the integral of f t into delta t minus a over the interval minus infinity to infinity gives us f a, the value of the function f at the point a. Now, let us take a particular case, let us assume f t to be equal to e to the power minus s t. Then it follows that L of delta t minus a is equal to e to the power minus a s. So, if you take f t equal to e to the power minus a s in the integral, then Laplace transform of delta t minus a, Laplace transform of delta t minus a will be integral 0 to infinity e to the power minus s t into delta t minus a dt. So, that will give us e to the power minus s, because we have shown that integral over minus infinity to infinity f t delta t minus a dt is equal to f a. So, from that f t equal to e to the power minus s t will transform to f a, that is e to the power minus s. Laplace transform of delta t minus a is e to the power minus s. Now, if you take a equal to 0 here, then we get that Laplace transform of delta t is e to the power 0, that is 1. So, Laplace transform of delta t function is equal to 1, or we can say that inverse Laplace transform of 1 is equal to delta t. Now, which is a very useful result. Let us take an example on this Dirac delta function. Let us find the integral of f t into delta dash t minus a over the interval minus infinity to infinity. We shall see that it is equal to minus f dash a. Now, making use of the integration by parts, integral over minus infinity to infinity f t delta dash t minus a dt can be written as f t into delta t minus a evaluated at minus infinity and plus infinity, and then minus integral over minus infinity to infinity f dash t into delta t minus a dt. Now, delta t minus a is defined as 0, everywhere except at t equal to a, where it takes value infinity. So, this will change, go to 0 as t goes to infinity or minus infinity, and the right hand side will then become. So, we get the integral over minus infinity to infinity f t eta dash t minus a dt equal to minus f dash a, because this becomes 0 as t goes to plus infinity or minus infinity, and this we have earlier seen that if f t is continuous at t equal to a, then integral over minus infinity to infinity f t delta t minus a dt is equal to f a. So, from that we get the value of this integral as f dash a. So, we get the value of the desired integral as minus f dash a. Now, let us find the Laplace transform of t cube into delta t minus 4. So, Laplace transform of t cube into delta t minus 4 is equal to integral 0 to infinity e to the power minus s t into t cube into delta t minus 4 dt. Now, so what we have now? We have this can be identified with the integral over minus infinity to infinity f t delta t minus a dt. So, here a is equal to 4, and that integral over minus infinity to infinity f t delta t minus a dt will then reduce to 0 to infinity, because over the interval minus infinity to 0 delta t minus a will be equal to 0. So, that integral, if you identify this integral with that, this will be equal to the value of this integral will be equal to e to the power minus 4s into 4 cube. If this is, we can regard this as f t, then it will become f a is equal to 4 here. So, the value of the integral will be 4 cube e to the power minus a s. A similar case is here. If you take integral over minus infinity to infinity sin 2 t delta t minus pi by 4 dt, then the value of this integral, again by this property of the Dirac delta function, that integral over minus infinity to infinity f t delta t minus a dt is f a, we will get the value of the given integral, that is integral over minus infinity to infinity sin 2 t delta t minus pi by 4 dt as sin 2 times pi by 4. This is sin 2a is equal to pi by 4. So, sin 2 pi by 4, and which is sin pi by 2, and we know that sin pi by 2 is equal to 1. Now, we shall study the example of a differential equation where the Dirac delta function is used. Let us solve the differential equation by double dash plus by equal to delta t minus a, where we are given that by b equal to by 0 equal to 0, a and b are some real constants. So, let us take the Laplace transform of the given differential equation. We will get Laplace transform of, using linearity of the Laplace transformation, we get the Laplace transform of the left hand side as Laplace transform of by double dash plus Laplace transform of by. So, Laplace transform of by double dash we know is given by s square by bar minus s by 0 minus by dash 0, and Laplace transform of by is by bar. Laplace transform of the right hand side, that is Laplace transform of delta t minus a, we have seen it is given by e to the power minus a s. So, now we can, let us take the, because we are given no value of y dash 0. So, let us assume that y dash 0 is equal to k, then we can find the value of y bar, solve this equation for y bar, and we get y bar equal to e to the power minus a s plus y dash 0, that is e to the power minus a s plus k divided by 0 is given equal to 0. So, we get y bar equal to e to the power minus a s plus k over s square plus 1. Now, let us take the inverse Laplace transform of the Laplace transform of y bar. We shall have y equal to sin t minus a into u t minus a plus k sin t. We can then use the initial condition, that is y at b is equal to 0. So, when you put t equal to v here, we get 0 equal to sin b minus a into u b minus a plus k sin b, and therefore, the value of k is equal to minus sin b minus a into u b minus a over sin b, and hence y is equal to sin t minus a into u t minus a minus k value of k is minus sin b minus a u b minus a over sin b. So, this value we are substituting here, So, bi is equal to sin t minus a into u t minus a minus sin b minus a into u b minus a over sin b into sin t. Now, let us study some applications of the Laplace transformation. First, we study the applications of the Laplace transformation to the problems in dynamics. Let us consider the case of a particle of mass m, which can perform small oscillations about a position of equilibrium under a restoring force m n square times the displacement. It is started from rest by a constant force F, which acts for a time t and then ceases. Show that the amplitude of subsequent oscillations is given by 2 f over m n square into sin n t by 2. So, let us say this is the position of equilibrium at O, the particle was here, at time t the particle is here, the mass of the particle is m, and at time t it is at a distance x from the position of the equilibrium, that is O, acted upon by forces, this is restoring force m n square x, and this is the force F, which is acting for a time t. So, the force F, which is acting for the time t only, can be represented as, and then it ceases afterwards, can be represented in terms of unit step functions as f into 1 minus u times 1 minus u t minus t, and therefore, the equation of the motion of the mass m will be equal to m x double dot, that is m into d square x by dt square, equal to resultant of the force F, which is acting for the time t only, and then the restoring force. So, we get m d square x by dt square equal to minus m n square into x plus f times 1 minus u t minus t. Now, dividing by m, we get d square x by dt square plus n square x equal to f by m into 1 minus u t minus t. Let us now take the Laplace transform of both sides. Laplace transform of x double dot or x double dash will give us s square x bar minus s x 0 minus x dash 0. X 0 is equal to 0 because at the time t equal to 0 the particle was at the point O and it was at the at rest. So, x dash 0 is also 0. So, making use of those initial conditions, we get the Laplace transform of the equation of motion as s square plus n square into x bar equal to f over m s into 1 minus e to the power minus s t. The Laplace transform on the right hand side, we get the Laplace transform of 1 is 1 over s, and Laplace transform of u t minus t as e to the power minus s t over s. So, the Laplace transform of the right hand side gives us f over m s into 1 minus e to the power minus s t after we make use of the given initial conditions, that is x at t equal to 0 is 0 and x dash at t equal to 0 is 0. Now, solving for x bar, we get x bar equal to f into 1 minus e to the power minus s t over m s into s square plus n square. Let us break it now into its partial fractions. We can write x bar further as f into 1 minus e to the power minus s t over m, and then 1 over s into s square plus n square. When we break into partial fractions, we get 1 over n square times 1 over s minus s over s square plus n square. Now, in order to find the displacement of the particle m from the position of equilibrium x, in order to find x, let us take the inverse Laplace transform of this equation. So, then we will get x equal to, now f over m n square, f over m n square is a constant. So, we have kept it like that only, f over m n square. Then this 1 multiplied by 1 over s minus s over s square plus n square. When we take the inverse Laplace transform of that, we get inverse Laplace transform of 1 over s as 1, inverse Laplace transform of s over s square plus n square as cos n t. So, we get 1 minus cos n t as the inverse Laplace transform of this expression. So, 1 into this whole thing, when we take the inverse Laplace transform of that, we get 1 minus cos n t, and then minus this minus is here, then e to the power minus s t multiplied by this. Then we take inverse Laplace transform of e to the power minus n e to the power minus s t into this expression by second shifting theorem will be equal to 1 minus cos n t minus t into u t minus t. Now, we can study the various cases here. When t will be more than 0, but less than capital T, u t minus t, the unit step function u t minus t will take value 0. So, x will be equal to f over m n square into 1 minus cos n t, and when t will take value more than capital T, u t minus t will be equal to 1. So, the displacement x will be equal to f over m n square into 1 minus cos n t minus 1 minus cos n t minus t, and this can be simplified further as f over m n square into cos n t minus cos n t. Now, making use of the formula cos a minus cos b as 2 sin a plus b by 2 into sin b minus a by 2, we get this expression further equal to f over m n square into 2 sin n t by 2 into sin n t minus t by 2, and thus the amplitude of the oscillations of the mass m about the position of equilibrium will be equal to 2 f by m n square into sin n t by 2. Now, let us study another example on dynamics, where a body falls from rest in a liquid. The density of the liquid is 1/4 of that of the body. If the liquid offers a resistance proportional to the velocity of the body and the velocity approaches the limiting value of 9 meters per second, then let us find the distance which the body falls in 5 seconds. So, this is the liquid and this is the body of mass m. After it has fallen in the liquid, mg is the weight of the body acting downwards, 1 by 4 times mg, 1 by 4 times mg, body falls whose density is 1/4, density of the liquid is 1/4 of the density of the body. So, we get 1 by 4 mg acting upwards, and then mkb, and 1 by 4 mg is the upthrust which is acting upwards, and then mkb, we are taking the resistance is proportional to the velocity. For convenience, we are writing resistance as mk into v, v is the velocity, the constants of proportionality we are writing as m into k. So, that we may cancel this m from the equation, we can divide that equation by m. So, for convenience we are writing the resistance equal to mkb. So, mkb is acting upwards, 1 by 4 mg is acting upwards which is the upthrust, and then mg which is the weight of the body is acting downwards. So, these are the forces that are acting on the body at a time t after it has fallen a distance x from the surface of the water. The x is measured from the surface of the liquid. So, this is the situation after and at an instant t, and thus the equation of motion will be given by m into dv by dt equal to mg minus 1 by 4 mg minus mkb. This is the resultant force acting on the body, and the m into dv by dt is therefore equal to the resultant force, which gives us the equation as dv by dt plus kb equal to 3 by 4 g after we divide the equation by m and simplify it. The initial condition is that at t equal to 0 the body was at rest, that is v was equal to 0. And let us now take the Laplace transform of this equation. When we take the Laplace transform here, the Laplace transform of dv by dt will give us s into b bar minus b0, b0 is equal to 0, and then k times b bar, and then 3 by 4 into g is a constant, then L of 1 is 1 by s. So, this is what we get after taking the Laplace transform of this equation, and we can then find v bar from here. B bar will give us 3 by 4 into g by s into s plus k. Let us bracket into its partial fractions. B bar will be 3g by 4k into 1 by s minus 1 by s plus k, and when we take the inverse Laplace transform of this equation, we shall have the value of v, which is 3g by 4k into 1 minus e to the power minus kt. Inverse Laplace transform of 1 by s is 1, and inverse Laplace transform of 1 over s plus k is e to the power minus kt. Now, when t tends to infinity, e to power minus k t will go to 0. So, b will tend to 3 g by 4 k. The limiting velocity of the body is therefore 3 g by 4 k, but we are given that the limiting velocity is 9 meters per second. So, thus we have 3 g by 4 k equal to 9, or we have k equal to g by 12, and hence v equal to 3 g by 4 k into 1 minus e to the power minus k t implies that dx by dt is equal to 9 into 1 minus e to the power minus k t. We know v is equal to dx by dt, and 3 g by 4 k is equal to 9. So, we get the differential equation again, dx by dt equal to 9 times 1 minus e to the power minus k t. Let us call this as equation number 1. And the initial condition is that when t equal to 0, the body was at the surface of the liquid, that is x is equal to 0. So, now Laplace transform of, if you take the Laplace transform of the equation 1, we are going to solve it for x. So, then we will have s x var minus x 0 is equal to 0, and the right hand side will give us 9 times Laplace transform of 1 as 1 over s minus Laplace transform of e to the power minus k t as 1 over s plus k. Or we can say that x bar is equal to 9 into 1 over s square minus 1 by s into 1 by s minus 1 over s plus k, after we break it into partial fractions. So, the inverse Laplace transform of this equation then gives us x equal to 9 times inverse Laplace transform of 1 over s square is t, and then we have minus 1 over k. 1 over k is equal to 12 over g, this is the value of 1 over k, and then 1 over s, inverse Laplace transform of 1 over s is 1, inverse Laplace transform of 1 over s plus k is e to the power minus k t, and k is equal to g by 12. So, we get e to the power minus k t as e to the power minus g t by 12. Now, let us put t equal to 5 and g equal to 9.8 meters per second square in this expression to find the value of x, which will give us the distance the body traveled by the body in 5 seconds. So, we get x equal to 9 into 5, that is 45. Then we calculate the value of this, 1 minus e to the power minus g is 9.8, t is 5 divided by 12. The value of this expression comes out to be 1 minus 0.017, and then 9 times 12 by g, 9 times 12 by g gives us 11.02. So, we get the value of x as 34.17 meters. Now, let us study some problems on the simple electric circuit. A simple electric circuit consists of a resistance given by R, inductance L, and a capacitance C, which are connected in series, and a switch is provided to connect or disconnect the circuit, and then a source of electromotive power is also there. So, then if we know that if q is the charge on the condenser at time t and I denotes the current in the circuit at time t, then q is equal to, then dq by dt is equal to I, and the voltages developed across the resistance, inductance and capacitance are given by L di by dt. L di by dt is the voltage developed across the inductance, Ri is the voltage developed across the resistance, and q by c is the voltage developed across the capacitance, which is equal to the electromotive source which is provided in the given circuit. Here it is in this problem, it is E delta t. So, by Kirchhoff's law, the L di by dt plus Ri plus q by c will be equal to E delta t, and dq by dt will be equal to I. Now, we are further given that it is also assumed that the connecting wires have negligible resistance. So, if I is the current at any time subsequent time t, we have to find the limit of I as t tends to 0. Now, let us solve these equations using the Laplace transformation method. So, when we take the Laplace transform of this equation, we will get this L is the this L is a constant. So, L times Laplace transform of di by dt, and Laplace transform of di by dt will give us s into I bar minus I 0. I 0 is equal to 0 because we have 0 initial conditions. So, at t equal to 0 the charge on the condenser is 0, and at t equal to 0 the current in the circuit is also 0. So, we get L into S into I bar plus R times I bar plus Q bar over C. C is the capacitance which is constant. The Laplace transform of Q will be Q bar equal to E times Laplace transform of delta t. We have seen earlier that it is equal to 1. So, we get Laplace transform of E delta t as E, and Laplace transform of dq by dt will be S into Q bar minus Q 0. Q 0 is equal to 0, and which will be equal to I bar. So, this equation, when we take the Laplace transform of this equation, we will get S Q bar equal to I bar, and hence we get the equations, following equations: L s plus R into I bar plus Q bar by C equal to E, and S Q bar equal to I bar. Now, substituting the value of Q bar from here as I bar over S in this equation, we will have the following: L s square plus R s plus 1 by C into I bar equal to E s, which can be expressed as S plus m whole square plus n square into I bar equal to E by L into S after dividing by L, where m is equal to R by 2L and n square is equal to 1 by CL minus R by 2L whole square. And we can then express this equation as I bar equal to E by L. S we can write as S plus m minus m over S plus m whole square plus n square. We have added and subtracted m here in order to take the inverse Laplace transform of this equation. So, when you take the inverse Laplace transform of this equation, inverse Laplace transform of I bar will give us I, E by L is a constant, and then inverse Laplace transform of this expression will be inverse Laplace transform of S plus m over S plus m whole square plus n square minus inverse Laplace transform of m over S plus m whole square plus n square. Inverse Laplace transform of S plus m over S plus m whole square plus n square will be e to the power minus m t into cos n t, because Laplace transform of cos n t is S over S square plus n square, and here S is being replaced by S plus m. So, by first shifting theorem, inverse Laplace transform of this will be e to the power minus m t into cos n t, and similarly inverse Laplace transform of m over S plus m whole square plus n square will be e to the power minus m t into sin n t. So, after taking inverse Laplace transform, we get I equal to E by L into cos n t minus m by n into sin n t into e to the power minus m t, and we then have as t tends to 0, the limit of I is E by L. Thus, we have the following remark that even though at initially the current was 0 in the circuit, I 0 was equal to 0, a large current develops instantaneously in the circuit due to the impulsive voltage which is applied at t equal to 0, and we are finding the limit of that is E by L. The E by L is the limit of this current which develops instantaneously in the circuit due to the impulsive voltage. So, E by L is the limit of this current as t tends to 0. Now, let us take one more example on this RLC circuit. The flow of current I in the RLC circuit when the initial electromotive force is E t is governed by the differential equations d I by dq by dt equal to I and L d I by dt plus R I plus q by c equal to E t, and when we take the Laplace transforms of the above equations, we get S q bar equal to I bar plus R I bar plus q bar by c equal to E bar. So, here we are studying a general case where E t denotes the electromotive source of voltage, E t denotes the voltage of the electromotive source. So, here we are assuming that I and q both are 0 at t equal to 0, and when we eliminate q bar from these two equations, or we put the value of q bar as I bar over s from this equation into this equation, we will get s square plus r by l into s plus 1 by l c into I equal to E bar s over L. So, E bar is the Laplace transform of E t. So, this can be written as s plus m whole square plus n square into I bar equal to E bar s by L, and where m is r by 2l, n square is 1 by L c minus r square by 4l square, as we had seen earlier, and therefore, I bar is equal to E bar s over s plus m whole square plus n square into L after solving for I bar. And when we take the inverse Laplace transform of this equation, we can then find the value of the current I. If at t equal to 0, now let us study some particular cases of the electromotive source of voltage E t. If we assume that at t equal to 0 a constant voltage E is applied, that is E t is equal to a constant E, then we will get I as, after taking inverse Laplace transform, E t is equal to E. So, E bar will become E by S, and therefore, E bar S will be equal to E. So, we will have E here, and then inverse Laplace transform of, so 1 over s plus m whole square plus n square will be e to the power minus m t into sin n t by n, and so I will be equal to E upon n l into e to the power minus m t into sin n t. Now, if 1 by L c minus r square by 4 l square is equal to 0, that is, if r, l and c have values such that 1 by L c becomes equal to r square by 4 l square, we will have the inverse Laplace transform of this equation as, because in that case n square will be 0. So, we will have I bar equal to E bar s over s plus m whole square into L. So, when we will take the inverse Laplace transform, the inverse Laplace transform of I bar will be I, and we will get E bar s is equal to E. So, we will get E here, L is a constant, it will come like that, and then 1 over s plus m whole square. Inverse Laplace transform of 1 over s square is equal to t. So, by first shifting theorem, inverse Laplace transform of 1 over s plus m whole square will be equal to t e to the power minus m t. And if it so happens that r, l and c have values such that 1 by L c becomes less than r square by 4 l square, then the n square which is occurring here will be replaced by minus k square, and will then have I bar equal to E bar s over s plus m whole square minus k square into L. So, then when we will take the inverse Laplace transform, we shall get I equal to E upon k l into e to the power minus m t into sin hyperbolic k t, because we know that the Laplace transform of sin hyperbolic k t is k over s square minus k square. So, when we multiply by e to the power minus m t and take the Laplace transform, we will get k over s plus m whole square minus k square, and so inverse Laplace transform here will give us I equal to E by k l into e to the power minus m t into sin hyperbolic k t if n square is equal to minus k square, and where we are assuming that 1 by L c minus r square by 4 l square is less than 0. Now, in our next lecture, we shall discuss some more applications of the Laplace transformation, like the application of Laplace transformation to bending of beams, and the application of Laplace transform to the boundary value problems which occur in engineering mathematics. We will find the solution of the heat conduction equation by using the Laplace transformation method. Thank you.